Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 4 from the January 2014 Core Mathematics C34 paper. It's like 10 years old now. This is related to P3, the syllabus about functions and range in domain and stuff like that, and composite functions. It's all to do with those type of questions, and it's a question that I've chosen because it goes through a few of the doubts that people have in this topic, and I'd like to just address those doubts and make sure that I can clarify some of those for some of the students who watch this video. So first of all, we're given two graphs. We've got the graph of this function, which is a modulus function, y equals f of x, and the graph of this kind of looks like it could be a exponential, or could be a reciprocal function. We'll see in a minute. It's actually a reciprocal function. Okay, so we have these two graphs. We have f of x, which is a modulus function, g of x, which is a reciprocal function, and first of it says find the value of fg1. Again, as I always say, it's very important to look at these parts here. These tell you about the domain of each function, okay, what values can go into them, and of course that will affect what comes out of them, right? So they're not here for decoration to make the question look kind of nice or whatever. They're here for a reason. So you have to take care of that reason, right? So now, first of all, it says find the value of fg1. So basically what that means is pretty simple. You have to just take the function g and replace the x with 1. Okay, so fg1, it means basically put g1 into function f. So into function f goes what happens when you replace 1 with x in function g. So you take the x plus 9 becomes 1 plus 9 over 2x plus 3 becomes 2 times 1 plus 3. Okay, and that gives us 1 plus 9, which is 10, over 2 plus 3, which is 5, which is 2. So that gives us f2. So we have to now put 2 into function f. All right, so 2 goes into this function f. So instead of the x, you write a 2. So 2 times the modulus of 3 minus 2 plus 5. Okay, and you can see that this is a valid input for function g, and this is a valid input for function f, because the domain of g must be any value of x greater than 1, and the domain of s must be any value of x greater than or equal to 0. Okay, so for both of them greater than or equal to 0. So the input of function g was 1, that's fine. The input of function f is 2, that's fine. Okay, it fits with the domain. All right, so that's going to give us 2 times the modulus of 1 plus 5. Now the modulus of 1 is 1, so you have 2 times 1, which is 2, plus 5, which is equal to 7. So we can say that fg1 is equal to 7. So always this goes into there, and the output of that goes into there. Okay, and you get your answer. That's fg1, and that's the answer to part 1 of this question. Now, or part A of this question. Now we're going to move on to part B. Okay, now for part B of this question. In this question, we are asked to state the range of function g. Now this is function g. Now, the diagram that they gave us, which is over here for function g, okay, is going to help us a lot in this question. So I'll just copy and paste it here, so we might need it later on as well. Put it back here. Okay. So this diagram actually has done us a lot of favors. We can see from this diagram exactly how to answer this question in a quick way, right? Now I'm going to show you two ways of answering this question. I'm going to show you the really long way, to get you to understand why what we write down is what we write down. Okay, and I'm going to show you the way that you would do it in the exam, which is right now I'm going to show you. Especially they gave us this sketch. I know that this function is valid, or the domain of this function is x is greater than or equal to 0. So it doesn't exist before this. So at this point, to find the range, remember, is the output of this function, the y values it can take. So you can see that it reaches the limit of this point over here. It doesn't go higher than this, and it doesn't go lower than something down here. Now you might think that the value down there, the asymptote that it has down there, is going to be the x-axis, but in fact it's not. I can see it's a half just by looking at the equation. I know that that is going to be y equals a half as the asymptote here, the horizontal asymptote. asymptote. Just by looking at the equation, I can see that. Okay, so this is the line y equals a half, and I'll show you how I got that in a minute. All right, so first of all, this upper limit is found by replacing x equals 0 into the equation. So when x equals 0, the y value will be 0 plus 9 over 0 plus 3, which is 3. So that is like the upper limit of the range of this function. With this limitation, it cannot go higher than 3. That's the highest it can get to. And I know the horizontal asymptote is going to be y equals a half. Why? Because if I take the coefficients of x on the numerator and the denominator, I'll get 1 over 2. So y equals 1 over 2. That is the horizontal asymptote. Okay? That's the value of y. If you put it into this equation, it will cause it to be undefined, as you'll see. If I put a half instead of y, and you try to solve it, it will give you something which doesn't make sense. So if I multiply both sides by 2 plus 3, I'm going to get x plus 3 over 2 equals x plus 9. Now, when I try to solve it, what happens is the x terms just completely disappear, and you're left with like 0 equals 9 minus 3 over 2, or 3 over 2 equals 9, which doesn't make sense. It's called a contradiction. So basically, you can see from, the equation like this. If you choose a value of y, which causes this coefficient to become the same as that coefficient, what's going to happen is when you try to solve, the whole equation will fall apart. Okay, if you end up with x plus something equals x plus something, the x's will cancel each other out. All right, so that's one way of looking at it, which you can see that basically it's going to be what you get when you divide these two coefficients. Basically what's going to happen. So that's a quick way of working it out. So we know that the asymptote horizontally is y equals a half. So we know it goes between a half, not equal to a half, up to 3. So that is the range of the function, and that's the answer to the question, 2 marks. Okay. Now, supposing you had a question where they didn't give you a sketch, okay, and you didn't understand those little shortcuts there. I'm going to explain it in a different way. Okay. Supposing they gave us a function like this to draw, and they didn't even give us this part for the beginning. We just basically were told to draw this function. Now, there's something that they would write here in that case, which won't be the same as this, something else. Okay, and we're going to discuss that now. Supposing the question says, find the range of this function, okay, and it was like this with no limitations except for something which we're going to talk about in a minute. Now, first of all, we have to try to recognize what type of function is it. Is it a function which is linear? Is it quadratic? Is it cubic? Is it exponential? Is it a function which is reciprocal? Whenever you have x in the denominator, you know it's going to be a reciprocal function. Okay, something over x. So we know that this is a reciprocal function. And as soon as we understand it's reciprocal, then we understand it's going to have what are called asymptotes. Okay, and there's 2 types of asymptotes. You have your vertical asymptotes, which are the ones that are easy to understand maybe why they're asymptotes. And then you have your horizontal asymptotes, which a lot of students don't understand why they're asymptotes, which I'm going to now explain. The vertical asymptotes are the ones which say x equals something. And that's pretty easy. You go to the denominator of the function. You go to the denominator. If that denominator ever becomes 0, then the function is undefined. So any value of x that causes the denominator to become 0 is going to be a vertical asymptote. X equals that number will be a vertical asymptote. So if you write 2x plus 3 equals 0, equate the denominator to 0, x is going to be minus 3 over 2, minus 1.5. So that's why this question would have something like this. Otherwise, it won't be a function. It will say x cannot be equal to negative 1.5. That should be mentioned in the question for you, all right, for it to be a function. You have to take out any undefined values for x. Okay. Any values of x that cause the function to be undefined. So that's going to be x equals minus 1.5. That's going to be the vertical asymptote. So we can make a little sketch now and just start putting things in place. Right, so we'll have our asymptote at minus 1.5. That's the vertical asymptote. In this particular question, it didn't really matter because our graph started kind of to the right of this. Started from 0. But minus 1.5, x equals minus 1.5 would be the vertical asymptote. Okay, now, the other type of asymptote is the horizontal asymptote, which I'm going to deal with here. Now, the horizontal asymptote, if we have y equals x plus 9 over 2x plus 3. Now, there's basically, it's going to be the value of y which causes this equation to break down and not to be able to be solved. And that's basically going to be the value of y, which when you try to solve the equation, will cause this coefficient of x to be the same as that coefficient. So that then when you try to solve it, it's going to become 0. So if I, for example, put y equals a half, and I have this x plus 9 over 2x plus 3. If I try to solve this, what's going to happen is, you can think about cross multiplication. This is going to become 2x plus 3 equals, and this has become 2x plus 18. Now what happens when you try to solve this? You bring the x's together, you're going to get 0 equals 18 minus 3, which is 15. Now 0 equals 15 is called a contradiction. There's no solution to it. So the value of y equals a half caused a contradiction in this equation, and therefore y cannot be equal to a half, which means that the horizontal asymptote is going to be y equals a half. And that's why y equals a half was the asymptote. Okay, so you have here y equals a half being our asymptote. All right, so that's one way of working out the asymptote is going to be a half. And now, as I mentioned, you don't even have to go that far, okay? Because what will always happen is it's always going to be the number that you have to basically, the number that is the result of the x coefficients divided. So the coefficient of 1 for x over 2, a half, that will be that number. Okay, always work out like that, okay? So that's something you'll understand. Another way to understand it is to split this up into separate fractions, which is a bit more hassle, okay? But you can still do it. I mean, if you can do it by long division, you can also do it by what's called split by what's called rewriting the numerator. So you can write this as 2x plus 3, and on top you just copy the denominator as 2x plus 3, and then you try to make this look like this. So this 2x plus 3 has to become x plus 9. So the first thing is we can multiply the 2x plus 3, can multiply this bracket by a half. That's going to give us x, which is what we want, but we're going to have 3 over 2. So we'll end up with, this will give you x plus 3 over 2, but we want to add something to that. That's going to give us 9. Now 9 is the same as 18 over 2. So if you add 15 over 2 to 3 over 2, you end up with 9. So basically you can say that this is the same as saying a half times 2x plus 3, okay, plus 15 over 2 divided by 2x plus 3. Right, that's now the same as this. Okay, that's the same as what we started with now, basically. That's going to give you x plus 3 over 2 plus 15 over 2, which is x plus 9. But now what we can do is we can split it now into two separate fractions. You can have a half times 2x plus 3 over 2x plus 3 plus 15 over 2 over 2x plus 3. Now the 2x plus 3's cancel out here, so you're left with y equals a half plus, and you're going to have 15 over 4x plus 6. This is the same fraction as that, but just written as split up into what's called a mixed number. This is like an improper fraction, where the numerator and the denominator have the same order, or the numerator sometimes has an order greater than the denominator. In this case, they're the same order. So it's an improper fraction. We've changed it into a mixed number. So we can see that, you know, it's kind of like of the form a plus b over 4x plus 6. So what makes the denominator here 0 is going to be the x asymptote. So that's going to be 4x plus 6 equals 0. So x equals, again, minus 3 over 2. That's minus 1.5, as we said. But this is going to be the y asymptote. Why is that the y asymptote? Because the value of y that you put here, which causes this equation to break down, is basically the same number as that's what's here. Okay, whatever number is added to the whole of this, if you put that number as a value for y, what will happen when you try to solve it, you'll have a half minus a half, which is 0, equals 15 over 4x plus 6. Now, when you cross multiply, you end up with 4x plus 6 equals 15, times 0 equals 15. Or you can say, 4x plus 6 equals 15 over 0. But in this case, you'll end up with 0 equals 15, which is another contradiction. That means the value of y, that's a half, is the value of y which causes this contradiction to occur. So y equals a half is the asymptote. So if you were to draw this function without any of the restrictions, it will have these two as asymptotes. Now, how do we work out where it goes? Does it go this way or does it go that way? Well, you can simply find out by putting, for example, when you replace x with 0, you're going to get 9 over 3, which is 3. Okay, so it must go this way. Okay, it must go this way. Okay, and if you want to do the same over here, you want to find where it hits the x-axis, you can put y equals 0. When you put y equals 0, you have 2x plus 3. You end up with x equals negative 9, don't you? Yeah, if you put y equals 0, you have x plus 9 equals 0, because when you cross multiplied, you made that 0. Ended up with x plus 9 equals 0, so x equals negative 9. So it's going to cross here at negative 9, and it's going to go something like this. That's how it would look if there was no restrictions. Okay, however, we had a restriction to the domain, which was this. Therefore, we have to get rid of everything. We have to make this a closed circle. And we have to get rid of everything that's less than 0. So we get rid of all of this, all of that. And that's how we end up with the graph that we had. Okay, that's how we end up with it. Okay, so that's something that's important for us to realize. So we don't have to go through all of this palaver really in this question. It's pretty simple for you to be able to even look at the sketch and work it out by putting some values in. And if they didn't give you a sketch, you can use those techniques that I mentioned. Okay, you can just, the value of x that causes the denominator to be 0 is going to be the x asymptote, which doesn't apply in this case because it's going to be way back here. And the value of y that causes this to have an asymptote is going to be when y equals a half, as we showed. So basically, it's going to be the same as the the coefficients of the x's divided by each other. So 1 over 2. Okay, so I hope you can understand the reasoning behind it rather than just memorizing it. But those are the reasons behind it. I hope that was clear because it's a very common question. So let's now go back to how I would answer it in the real exam. So get rid of all of this now. And let's go back to the actual question. So the actual question is only worth 2 marks. And in the exam, I wouldn't go through any of this palaver that I've just gone through. I'm just doing that in order for you to understand. Okay, I like my students to understand what's happening. So it's a very common question. Why, sir, is that the asymptote? And it's very good for you to ask that question. And it's something that I do think is important for you to understand what you're doing. All right, but in an exam, of course, that wouldn't be very sensible to write out all of those things. You can simply just, as long as you understand, you can simply understand that you're going to have the x asymptote doesn't actually affect the question, that we can see the range of the question is between here and here. There is an asymptote that we know is not 0. Okay, so there's definitely an asymptote which is not 0. And it's y equals a half, which is going to go over here. Let me put it lower so it doesn't touch the curve. Okay, so y equals a half is the vertical asymptote, the horizontal asymptote. So we know that the graph, its range is between these two values, a half and 3. So we can just write down g of x is less than or equal to 3, but greater than a half. And that's all it says state. That means you don't have to actually show any steps. You can just do that. But if you wanted to, it'd be good. You can say, okay, when x equals 0, y equals 9 over 3, which is 3. Okay, and you can say when y equals a half, you have the horizontal asymptote. That's fine. Okay, so there's the answer to part B. And that's really all you have to write. But what I had written out before and then I erased it all of that stuff is the reasoning behind it and a few different ways of thinking about that reasoning. Now for part C, it says find the inverse of the function g and state its domain. Okay, now in this question here, you got to be very careful, especially in like the newer papers. They don't actually sometimes mention this part. It will just say find the inverse of function g. And part of finding the inverse of the function is finding its domain. So you don't state the inverse function without stating also what its domain is. All right. So many questions will give you, they'll give you like this, find the inverse of function g without mentioning anything. If you just find the algebraic expression for the inverse without stating the domain, you could lose a mark or two. So you have to be very careful about that, especially in these new specification questions. In Cambridge, a lot of times they say, find an expression for the inverse of the function, which means they only want the expression, they don't want the domain with it as well. So it's very important for you to understand that. Whether it says this or it just says find the inverse, it means you have to do this anyway, basically. That's what you have to understand. Otherwise, you'll be liable to lose marks. Okay, so let's first of all deal with finding the expression for the inverse function. So we have g of x, x plus 9 over 2x plus 3. So the first step is, I'm writing in white, 1 second. The first step is to call the function y equals. So g of x becomes y equals x plus 9 over 2x plus 3. The second step, I like to do this right at the beginning here so that I don't forget the end, is to switch the x and y. Wherever it says y, it just is replaced with x. Wherever it says x, it's replaced with y. So you have x equals y plus 9 over 2y plus 3. And then the next step is to make y the subject. You've got to be very careful in doing so. So we'll multiply both sides by 2y plus 3. So we end up with x times 2y plus 3 equals y plus 9. We want to make y the subject, so we're going to now have to bring the y's together on one side of the equation. So what I can do here is I can expand this bracket, so that's going to be 2xy plus 3x equals y plus 9. And now I can I can bring the y's on one side, so I can say 2xy minus y equals 9 minus 3x. Okay, and then I can take y as common. So I have y times 2x minus, 2x minus 1 equals 9 minus 3x. And then I can say y equals 9 minus 3x over 2x minus 1. So that is the expression for the inverse. So we can say, therefore, the inverse function is going to be 9 minus 3x over 2x minus 1. Okay, we could also write it if we want. We can also write it if we want. If we had, for example, at this stage, decided at this stage to say, let's bring the y's on this side, then we would have got y. We would have got, basically, I'll just show you. We would have got this as alternative. We could have got 3x minus 9 is equal to y minus 2xy. And then 3x minus 9 equals y times 1 minus 2x. And then you have 3x minus 9 over 1 minus 2x. Okay, so you end up with your inverse function being 3x minus 9 over 1 minus 2x. They're the same thing. They're the same thing. It's just the numerator and denominator to be multiplied by minus 1. So either this or this can be your answer for the inverse function. Both of them are totally fine, depending on how you rearranged it. So they both will be acceptable as answers. Okay, and even if you did it in another way where you ended up having just one, what's the word, a mixed number, that would also be okay. But we'll leave it like that for these two versions. So that is the expression for the inverse. Now, the domain of the inverse, it's very simple actually. Okay, because we already have the range of the original, and the domain of the inverse, the domain of the original, the domain of the inverse function for g is going to be the same as the range of the original function. So the range of the original function is the domain of the inverse function. The range of the original function becomes the domain of the inverse function, okay? Because it's like you're swapping the x and y coordinates around. And you'll see, I'll show you how that works even with the equation in a minute. So basically, we can say that the inverse function could be this or that. So we'll write it like this, for example. And the domain is, now we write the same thing as we wrote here for the range of this function. Except we don't call it g of x, we call it x. Because it's the domain now. The domain is x values. So it's going to be the values of x which are greater than a half and less than or equal to 3. That will be the domain of the inverse function. Okay, so you don't have to show any steps for this. You have to just understand that when you have a inverse function, its domain will be the same values as the range of the original function, except you write x instead of g of x. Yeah, it's the x values. The domain is to do with x values. And I'll show you how it works from the equation as well. Let's look at this graph here. Okay, this is the graph of the original function. Okay, now the inverse function is always a reflection of the original function in the line y equals x. Okay, so these little points I'm making now are not to do with answering this particular question in the exam. It's just to further our understanding, and in case such questions come up like this, we will understand what to do. So remember, this was basically 3, and this asymptote was y equals a half. So when you have an inverse function, basically what happens on the x and y, they swap over. So the coordinates of this point, which is 0, 3, for the inverse, they become 3, 0. So on gx 0, 3 will become, on the inverse, 3, 0. The x and y swap around. So this is going to be going through 3 here. Okay. All right. It's going to be like starting from there. And the asymptote, which was y equals a half, the asymptote, which was y equals a half, becomes now x equals a half. Okay, so the asymptote now becomes x equals a half, which is going to be somewhere like this. Okay, just draw it a bit closer to that because it's close on that one. Whoops. I want to take this and move it like that. Okay. So this is now the vertical asymptote. I'll show you how that will work also in the equation. And they always intersect on the line y equals x. So this will look something like this. Oops. Let me start that one again. This will look, it's a bit difficult to draw here. Let me just adjust my position a bit. All right, so this is going to look something like this if we were to draw it. Recent question asks you to draw the inverse, so you should understand how to do this. So you can see it's a reflection in the line y equals x. So we can see here that the domain of this function is between a half and 3, not including a half, but including 3. It's the same as the range of this function, of the original function, which is between a half and 3. Okay, so the domain and the range just switch over. Okay, so how can we understand this algebraically as well? Well, for example, let's take let's take y equals, or the inverse of f equals 9 minus 3x over 2x minus 1. Now the vertical asymptote, for this is going to be whatever causes the denominator to become 0. All right, as we know, the vertical asymptote is what makes the denominator become 0. So when 2x minus 1 equals 0, x equals a half. So we can see x equals a half is the vertical asymptote, as we can see from how we understand from the graphs. This basically y equals a half becomes x equals a half. As we can see from the algebra, it also works, and also the value of the y value, which causes this equation to break down. Okay, the y value that causes this equation to break down is going to be basically minus 3 over 2. Minus 3 over 2. If you put y equals minus 3 over 2, you'll end up with this. How do we know that? Remember, we mentioned we divide the coefficients of x. Okay, so if you try to solve this, you get minus 6x plus 3 is equal to 18 minus 6x. So if you try to solve this, the 6x and minus 6x, they will basically cancel out. Okay, you have minus 6x plus 6x becomes 0. That will become something that says 3 equals 18, which doesn't make sense. So we can see that the vertical asymptote is x equals, the horizontal asymptote is y equals minus 3 over 2, which is outside of our particular diagram. Okay, but we can see it does make sense according to the original diagram we drew. There was an asymptote here, x equals 3 over 2, negative 3 over 2, which becomes now y equals negative 3 over 2. All right, so that makes sense. Okay, and yeah, so basically that's all we need, because if we know that there is an asymptote x equals a half, okay, at x equals a half, then we can see that this starts from 3, all right? Can't go any further than 3 because you can't go further than this. You can see, for example, you can see where does this hit the y-axis? Where does this hit the x-axis? This hits the x-axis, okay, when y is 0. So if you do 9 minus 3x over 2x minus 1 equals 0, you'll have 9 minus 3x equals 0. So 3x equals 9, so x equals 3. So you can see that according to the equation, this graph will hit the x-axis at 3. All right, and you know, because our domain is from 0, from a half to 3, we can't go further than that. So that's where it stops. So you can see that the algebra makes it hit the x-axis at the right place, puts the asymptotes at the right place, and you know, all of that. So that's how we can understand what to do. And for example, if the question said find the point where the inverse and the original intersect, then because they both intersect at y equals x, we could take any one of the two. I could take the original equation here, and I can just equate it to x. I could say x plus 9 over 2x plus 3 equals x, and it will give me the place where they intersect. Now, this is not part of the question, okay? Now, this is going to give me like 2x squared plus 3x. It's going to give me a quadratic, okay? Now, why would it give me a quadratic? Because they probably intersect over here as well, somewhere down here, because the, unrestricted, there'll be another 2 branches down here somewhere, okay? So you'd get 2 answers for this, and one that would be positive for x and y would be the answer that for this particular question, right? And you'd get the same answer if you put the inverse function and you equated that to x. It will give you the same values of where they intersect as well. All right, so that's how we can deal with that one. I'm not going to go into that in too much detail, but that's how you can find where the inverse and the original of function will intersect in such questions. All right, so there's a bit of background understanding of how to deal with the question, but really I'm going to cross out all the things now which we didn't really need to show to answer this question in terms of just if you were in your exam. Okay, we didn't have to do any of this drawing. Didn't have to talk about any of this stuff here. None of that stuff is necessary for us to get the marks, but it does help your understanding. That's the reason why I'm explaining it. A lot of students do ask about these things, so you don't even have to have the drawing of the graph there, to be honest. All you have to maybe state is you could say that the domain of the inverse of G is the same as the range of G of x. Okay, so therefore you can say the domain is, the only difference is you don't put G of x or inverse G of x, you put x. Domain is x values. Okay, so that's all you have to do. You do the algebraic expression for the inverse, and then you just copy the answer for the range exactly the same as it is as the domain of this, except you don't put f of x or g of x, you put x. That's it. Right, so it's a very quick question actually. I spent a bit of time to explain it because of, as I mentioned, I want the students to understand what's going on, and I get asked this a lot. So that's part C of the question. Now we're going to go on to part D. There is a part D, yes. It says, given that the equation fx equals k, where k is a constant, has exactly 2 roots, state the range of possible values of k. So here we have a modulus function. Okay. Now, the equation of this modulus function, f of x, is equal to 2 times the modulus of 3 minus x plus 5, and its domain is x is greater than or equal to 0. All right, so we need to find the range of possible values of k such that f of x equals k has 2 roots. So f of x equals k means y equals k. K is a constant. That means y equals k is basically just a line which is horizontal. It's a horizontal line. Okay, like this. Okay, So if we take a horizontal line on this graph and we put it in different places, if it's down here below the vertex of this, there will be no roots. This will never, the roots are for, f of x equals k, where these two, where basically y equals k and f of x intersect. Okay, the roots are basically the places where they intersect. So here there's no roots. When we're below the vertex, there's no roots. And at the vertex, there's, like, you could say, one repeated root. But above the vertex, there's two roots, two distinct places where they intersect. Okay, two distinct roots until we reach this place here, which is the y-intercept. If you go above the y-intercept, there's going to be only one real root, and that continues because this graph will continue on forever going up because it's got a range which is greater than 0, because this will carry on and on and on. So as far as this goes up, which will be infinitely, there will be only one real root after that, because this branch of the graph stops. It doesn't carry on. Okay, if this branch of the graph also carried on, then it would be from the vertex upwards that we'd have two real roots. But because this branch of the graph stops at this point over here, so the two distinct roots stop here as well. So the distinct roots are going to be between this range, these 2 points here. This is, let's call this y1 and y2. Okay, those are the two values for which, between those two values, there will be two distinct roots. Okay, two distinct roots. So when k is greater than this y value, and when k is less than this y value, between those values, there will be two distinct roots. I hope that's clear for you all. Okay, this is the line y equals k. So we got to find the values of these 2 points. So we need to find one, we need to find this point. Let's call it y2 first. That's called the y-intercept. Now the y-intercept is on the y-axis, and on the y-axis we know x equals 0. All right, and x can equal 0 here because it says greater than or equal to 0. So we're going to replace the x with 0. So we can say that the y2 is going to be given by 2 times the modulus of 3 minus 0 plus 5, which is 2 times 3 plus 5, which is going to be 11. So this is 11. Okay, so that's the upper limit. And the lower limit is the y value of the vertex. How do we find the vertex of this type of graph? Well, it's pretty simple. Okay, it's pretty simple. And I'll show you first what it is, and then I'll explain why. So we have, I'll write it as y equals 2 times the modulus of 3 minus x plus 5. So the x coordinate of the vertex is the x value that makes what's inside the modulus sign 0, which is going to be 3. And the y value of the vertex is what's left behind. When this becomes 0, you get 2 times 0 plus 5, which is 5. So I know that this is going to be 5 here. And I know that this point is going to be 3. Now, how did I know that? Well, it's similar to, you could say, if you had y equals 2 times 3 minus x squared plus 5. If you had something like this, which is a quadratic, completed the square form, you know that the x value that makes this bracket 0 is the x coordinate of the vertex, and what's left outside is the y coordinate of the vertex. The reason why that is because when you have y equals 5 plus 2 times 3 minus x squared, okay, you're always adding something to this 5. So it's y equals 5 plus something. This will never be something negative because you're squaring it. So you'll never have 5 plus 2 times minus something. You'll never have 5 minus anything. It's always going to be 5 plus something. So it's always going to be bigger than 5. Now the least amount you can add to the 5 is 0 when this becomes 0. What makes this 0? When x equals 3. When x equals 3, okay, you have 3 minus 3 is 0, and you're left with 5. So 3, 5 is the vertex. That's for quadratic, and it's the same, exactly the same thing for this. Why? Because the modulus sign acts like a square sign in the sense that it changes all negative values to positive values. So even if this comes out as a negative value, for example, if x is, 10, you'll have 2 times the modulus of minus 7. Well, the modulus of minus 7 is 7, so you'll end up with 2 times 14. You'll never subtract anything from 5. So this will always be 5 plus something. And the lowest amount you can add to that 5 would be when this whole thing becomes 0, which is when x equals 3. So x equals 3. When x equals 3, what are you left with? Y equals 5. That's why this is the lowest value. So we can say that the possible values of k are going to be between 5 and 11. We don't include 5 and we don't include 11 because, no, we do include 11. We do include 11. Why? Because there's two distinct roots here still. All right, but here at 5, it's like there's one root basically, because it's just 1 point. Okay, it's not 2 points. Here we have 2 points. One, as you can see, we have 1 point here and 1 point there. 2 points, two distinct points. But at 5, there's actually just 1 point. So just slightly above 5, we're going to have 2 points until 11. If you go above 11, straight away there's only one root then after that. Okay, so that's how we can understand how to write the answer. You've got to be careful with these inequality signs. So there is our answer to this question. That completes the whole question. I know I spent a long time answering this question. Okay, and some of you might be like, oh, what's he going on about for so long? But it's something which is important to explain for some students. As I said, I don't make these videos, for any particular person, or anyone's convenience. I make these videos as a teaching tool so I can explain concepts to my students and also sometimes other students who ask questions and they want some clarification about certain points. So I might go on and on about certain things, but I have a reason to do so. Okay, so if you're like just wanting to see what the answer is and the marks given, it might not be the right place for you. But if you're here to try to understand and learn some of the reasons behind things and stuff, then that might suit you. Okay, so anyway, I hope that was clear. Other questions from this particular paper can be found in the playlist that will appear on the top of the screen over here. Other questions from this topic of functions from P3 you'll find in the playlist over here. I'll also have a section of modulus function questions. I'll add this too, and you can subscribe to the channel by clicking on this link over here. Thank you for watching and see you soon.